The world is not a collection of snapshots. It is a stream. When you read this sentence, the word stream only has meaning because of the words that came before it. A single note in a melody means nothing in isolation. A doctor's single heart rate reading is useless without the pattern unfolding over time. Standard neural networks, the kind that identify cats in static 224 by 224 pixel images, have a fundamental flaw. They have amnesia. They process every input as if they've never seen anything before. To understand language, music, or stock prices, we need a network that remembers.
Here is the constraint. Feedforward networks demand fixed-sized inputs. Give them a standardized image and they work perfectly. But sentences? Hello is one word. The quick brown fox jumps over the lazy dog is 9. A paragraph from a novel is 100. You can't just pad everything to the same size and hope for the best. We need an architecture that handles variable lengths and maintains context. This is the recurrent neural network.
The breakthrough was simple: a loop. In a standard network, information flows forward: input, hidden layer, output. In a recurrent network, the hidden layer does something unique. It sends its output forward, but also sends a copy backward into itself for the next time step. This self-connection creates a hidden state, denoted as HT. Think of HT as the network's short-term memory. It is a compressed summary of everything the network has seen in the sequence so far. Let's look at the actual mechanism. At any time step t, the new memory, HT, is calculated using a specific formula, the activation function applied to, wait for it, the previous memory, HT-1, weighted by matrix WHH, plus the current input XT, weighted by matrix WXH. See what's happening? WXH processes what we see now. WHH processes what we remember from the past. They are added together and squashed by a tanh function. This is weight sharing. We use these exact same matrices at every single step. Whether the sequence is length 10 or length 1000, the model size stays exactly the same.
To really understand this, we need to unroll the network. Imagine taking that single recurrent cell and copying it once for every time step. At t equals 1, we process the first word. The state moves to t equals 2. We process the second word. The state moves to t equals 3. Even though it looks like a deep network growing to the right, remember, every one of these cells is actually the same cell using the same weights. This unrolled view is how we visualize the flow of time.
This idea evolved over decades. In 1982, John Hopfield, who won the 2024 Nobel Prize for this, showed that networks with feedback loops could act as associative memory. By 1986, Michael Jordan proposed feeding the output back into the network, remembering what it said, that this simple context loop could let a network implicitly learn the difference between nouns and verbs just by looking at word order. So how do we train this? We use backpropagation through time. First, we forward pass through the whole sequence. Then we calculate the loss. Finally, we propagate that error backward from the last time step to the first. Here is the catch. Because the weights are shared, the gradient for WHH is the sum of gradients at every single time step. For a sequence of 1000 steps, you have to run backprop through 1000 layers. This is computationally expensive, O of t. So in practice, we use truncated BPTT, splitting the sequence into manageable chunks of 20 to 200 steps.
But in 1994, Yoshua Bengio exposed a fatal flaw. When you backpropagate through time, you are essentially multiplying matrices over and over again, once for each time step. Mathematically, the gradient involves a product of Jacobian matrices. Think about it. If you multiply the number 0.9 by itself 50 times, you get 0.0005. Do it 100 times, and you get 0.00003. If the weight matrice's spectral radius is less than 1, the error signal shrinks exponentially. By the time the signal reaches the beginning of the sequence, it's effectively 0. The network knows it made a mistake at step 100, but it has no way to tell step 1.
The opposite can also happen. If that spectral radius is greater than 1, the gradients explode. They grow exponentially, turning into massive numbers that create NaN errors and destroy your model weights. Fortunately, this has a simpler fix: gradient clipping. If the gradient vector size exceeds a threshold, say 5, we simply scale it down to 5. We preserve the direction so the network still knows which way to learn, but we limit the step size to prevent a catastrophe.
Despite these challenges, RNNs offer incredible flexibility. We can do one-to-many, take one image and generate a sequence of words, image captioning. We can do many-to-one, take a sequence of words in a movie review and output a single sentiment score. Or many-to-many, language translation, where a sequence of French words produces a sequence of English words. The architecture molds to the data. Recurrent neural networks taught machines that context matters. By adding a loop, we gave neural networks a memory, allowing them to process the stream of reality rather than just static snapshots. While simple RNNs struggle with long timelines due to vanishing gradients, a problem that would eventually lead to LSTMs and transformers, they laid the foundation for modern sequence modeling. They proved that to understand the present, a model must maintain a connection to the past.